As I've shown in a previous video, the Altair Cassette Interface was actually a two-board set. It consisted of this serial interface board you see here. This is the 88SIO. This is what actually plugged into the bus, and the software actually talked to the UART on this card in order to do the serial communication with the cassette. And then attached to this board, piggybacked onto it with spacers and screws, was a slightly smaller modem board that converted to and from that serial data into the audio tones that were then on the cassette tape. Also in that video, we demonstrated a way to make a drop-in equivalent of this Altair Cassette Interface, but using hardware that was more readily available. And that's because this Altair Cassette Interface was fairly rare. So for example, in that video, the serial interface board we used was this blue board made by Solid State Music. This is their IO4 board. And it was very easy to configure to look identical to that 88SIO board that we just had up there, so the software could not tell the difference. Now this does not have the modem, of course. For the modem, we went with this little board you see here. This is actually the cassette interface board from the Altair 8800 clone. So this is a modern board, but it's pretty much the only modem board that I could even find that we could possibly do this with. So obviously we have a couple of audio connectors to and from the cassette, and then this header connects to a DB25, and then these two boards communicated with each other through RS-232 and those DB25s. All right, so on a related note, semi-related note, in another video I went ahead and showed another cassette interface board. It's this one you see here, made by Processor Technology. This is their CUTS board. And one big advantage of this board over the Altair board is that it ran at 1200 baud to cassette as opposed to the 300 baud that the Altair cassette ran. And it's also the 300 baud that all your Kansas City standard boards were starting to use at that point as well. So 4 times as fast as all these boards. So software that might take 4 minutes with the Altair cassette or 12 minutes with paper tape, it would load in a minute on this board. So that was a huge improvement. It felt much quicker than waiting the 4 minutes. Now, this board is obviously made for Altairs and S100 computers, but unfortunately, it's not compatible with the existing Altair software at that time. For example, Altair Basic or their assembly language programming system, those expected the Altair cassette hardware. And this had different I/O ports and different mechanisms for interfacing. So that same software couldn't use this board. Now, Processor Technology had some good software when we demonstrated that in a recent video, and I've put a link to that in the description of this video so you can learn more about it. But if you wanted to use the real Altair software, you couldn't take advantage of this board and its speed. So I thought it would be a fun project to see if I could take our drop-in equivalent hardware and somehow make it work at 1200 baud. So I would then have a 1200 baud 4 times as fast Altair cassette interface. And that's what this video is going to be about today. The first step in bumping from 300 to 1200 baud will be to get this serial interface board to run at 1200 baud. And as you might expect, that's pretty straightforward on a serial interface board. Here's the baud rate header that this board uses. This upper one controls the port that we use for the cassette, and I modified it to work at 1200 baud instead of 300. And at that point, this board is ready to go. The harder part, as you might guess, would be getting this modem to work with the cassette at 1200 instead of 300 baud. Now, the way the Altair board and the Kansas City standard boards all worked is they used frequency shift keying. What that means is that one frequency represents a 1, in this case 2400 baud. 2400 hertz, and then a 0 in the Altair is represented by 1850 hertz. In the Kansas City standard, a 1 was also 2400 hertz, but then a 0 was 1200 hertz. But very similar, you're just bouncing between those two frequencies to indicate a 1 or a 0. The CUTS board, the processor technology that worked at 1200 baud, also used 2 frequencies. One was 1200 hertz to represent a 1, and then 600 hertz represented a 0. But it doesn't take long to realize something's a little funny here, because at 1200 baud, you only get 1 cycle of 1200 hertz, and you only get a half a cycle of the 600 hertz signal per bit time. And clearly that's not enough for any PLL or anything like that to properly discriminate between the two frequencies without any errors. So what's really going on with this CUTS interface? It can't be FSK. And in the end, it's not. It's actually something much closer to how a single density floppy disk was written. Let's take a look over on a computer at some drawings to make this clear. All right, let's take a look at how the CUTS board demodulated a waveform coming off the tape into data. Here we're going to pull in a data stream that represents 1010. Coming off of a cassette for the 1, again, is a 1200 hertz signal like you see here, one cycle of it. For a 0, you get half a cycle of a 600 hertz waveform. Here's the 1, so we have a full cycle of a 1200 hertz waveform, and here's a 0, we have a half a cycle of a 600 hertz waveform. Now the demodulator then has a zero crossing circuit that for every rising or falling edge as it crosses 0, it generates a short pulse. And those are these pulses you see here. So in the end, we get a short pulse here at each bit boundary. We can kind of consider this a clock. We're getting one at every bit boundary, nice and steady at 1200 baud, 1200 hertz. If between the two clock pulses there is an intermediate pulse, then it's a data 1. If between the two clock pulses there is not an intermediate pulse, then it's a data 0. Now this may look very familiar to you if you're at all familiar with how floppy disk drives work. This is the same encoding used with single density floppy disk drives. They call it FM encoding. And again, it's not frequency based, even though they call it FM. It's more timing based. It is the position of these pulses to define the bit times and whether or not there's a 1 or a 0 by this intermediate pulse. So obviously this is totally different demodulation, analog and digital hardware, than you would have for the FSK system like the Altair. So why is it that I think that I could make my modem decode this if it's designed to decode FSK? Well, the reality is on that little cassette interface board, it never really worked in the frequency domain to begin with. Instead, it timed between 0 crossings to determine how long the period was of a waveform. If that period was the length of 2400 hertz, it knew it was a 1. If the period of the waveform was the same as an 1850 hertz, then it knew it was a 0. And so since that was already timing based, it wouldn't be hard to convert it to look at these 0 crossings and decode the data as it was done on the CUTS board. All right, now one problem that I ran into as I tried to implement this though is that I don't have as much analog processing on this little cassette interface board as they have on the CUTS board. I can't get negative going and positive going edges. I can really only get the rising edges on these. And so that doesn't allow me to actually time these out exactly like I need in order to generate this, because I can only get that edge, that edge, that edge, etc. So I modified this slightly, and I used 2400 hertz for a 1 and 1200 for a 0. And in the end, looking at just rising edges, I get the same thing. Here's a rising edge, gives me a pulse. Here's a rising edge, gives me a pulse. Here's a rising edge, gives me a pulse. Here's one, gives me a pulse. So by modulating between 24 and 1200 hertz and only detecting rising edge crossings of the 0 volt line, I can generate the exact same waveform that we had with the CUTS. So this is what I had to actually implement in the end. Very similar to CUTS, but again, I had to use 2400 and 1200 hertz. And obviously those are within the frequency bandwidth of the cassette player, because those are the frequencies used by KCS, except we're going to get 1200 baud out of them instead. Now, modifying that firmware to do these captures and generate this timing and demodulate in this manner was actually a very minor modification to how it already worked. And I was thinking, boy, this is going to be pretty easy. However, what I did run into is what was previously trivial, which was writing the data to the cassette, became much more complex. Let's take a look at that next. What you see here is all the code that was required to generate the waveforms that are written to tape for the original Altair FSK format. This is an interrupt routine from a timer that times out a half cycle time of a 2400 or 1850 hertz tone. So when the interrupt occurs, it comes in here, clears the interrupt, toggles the audio output to the opposite state, and then determines if it needs to do the period for a 1 or a period for a 0. Of course, the 1 is a half of a 2400 hertz, and a 0 would be half of a 1850 hertz period. And then it sticks that into the period register of the hardware timer and exits. And very simple. This thing just free runs all the time and automatically adjusts to whatever the data that's coming in. Now, there is no synchronization between this timer and the 300 baud crystal or whatever's running off of the serial interface board generating the data. And so there will be a beat frequency between them. And every time that beat frequency wraps around, we're going to have a half cycle of waveform that is wrong. However, that doesn't affect anything because there are numerous cycles per 3.3 millisecond bit time at 300 baud. And so that first lead-in or trailing half cycle that might be wrong every time we have a wrap of the beat frequency doesn't affect the data enough to make any difference. Now, going to this new system where we have a 1200 hertz signal at 1200 baud, there's only one cycle in there. We can't afford to drift at all, basically, but there's no easy way to be in sync with the 1200 baud from the serial interface board other than bringing wires over from the baud rate generator, which I don't want to do that. I don't want to have to change anything about the board other than firmware. So what I ended up having to do was essentially make a software PLL that did the transmission of the data. I could no longer use the hardware timer. Let's go ahead and take a look at that. Let's take a look at how this software PLL might work. Here's a sequence of incoming data from the serial board, 1101. Here's what that looks like electrically in its NRZ data. It goes from high for the ones down to zero, low for the 0, back high for the ones. And then here is the audio data that's being spit out by our little processor. 2400 hertz right here for the ones, 1200 hertz right here for the 0, back to 2400 hertz for the ones. Now these are square waves coming out of the PIC processor, but then there's a single node RC filter that rounds the edges up a bit before it goes to tape. All right, so basically what we want to do is every time we get an edge on the incoming data from the serial board, we want to sync our output data, this data here going generating the audio, to those edges. Now, as you can see, we don't get an edge for every bit position, every bit time, which is one downside of NRZ data if you're trying to do any sort of self-clocking application like this. However, since it is asynchronous data, that means we have a start bit and a stop bit around every byte of data. That means the longest run of ones or zeros is going to be 9 bits. As long as data is continually coming in, the longest sequence we'll have of all ones or all zeros with no edges, it will be 9 bits. And that's okay for this application. It can keep up with that and make adjustments that don't cause data errors. All right, so let's look at what kind of adjustments we'd need. We'll take a look at this edge right here. So this edge comes in and we will either be behind it or ahead of it, depending on whether we're running slower or faster than the baud rate crystal over on the serial interface board. All right, so let's go ahead and just simulate what this is going to look like. I'm going to shift this to the right a little bit, which would mean we're coming in late. So we're running a little bit slower than expected. So what we need to do is detect this edge occurs, look and see, oh, wait a minute, we're in the middle of a cycle that's about to finish, but we should really go ahead and finish it up early to get back in sync. All right, so that would look something like this. We're going to shrink that last pulse so that we start the next one in sync with the new data. And that realigns us. Here we're back in the middle, here we're back at the edge again. So that's what would happen if we were running a little bit slower. And of course, the other option, or the other case, would be you're running a little bit faster. So let me move this back to illustrate that. All right, so now we're done before the next bit edges actually come in. And we're started a half cycle of 2400 hertz here. We don't know that it's a 0 yet. So in this case, we see this edge come in. We look and say, I just started a new pulse, a new half cycle period. Therefore, I don't want to generate a new edge here. That would generate this really short pulse. What you want to do is extend the one that you're starting to get you back in sync again. So that would look something like this. So this pulse edge that we now know is a 0 because we saw the edge come in, we're going to extend that one a little bit more than normal, so that gets us right back in the middle, right back on the edge with that resynchronization. And of course, you're going to do this again on this edge, and it will be a smaller tweak than previously, but all these little tweaks keep us in sync the whole time. So that's basically how the PLL has to work. Basically, those two cases. I'm either a little bit ahead, and therefore I need to extend the next cycle, or I'm a little bit behind, and therefore I'll just start the new cycle a bit early. To implement this software PLL, I'm going to sample the incoming data from the serial interface board 64 times per bit period. That ends up being a 13 microsecond interval in between samples. And that same tick, that 13 microsecond tick, can be used to time the audio cycles that we're generating. For audio, we generate a half a cycle high, half a cycle low. So for 1200 hertz, a half a cycle would be 32 of these ticks. For the 2400 hertz we have to generate, a half cycle would be 16 of these ticks. Now we have this PLL divided into two loops. One for while the RS-232 input from the serial board is a 1, and then a virtually identical one while it's 0. So these are almost mirror opposites of each other. So let's take a look at the loop while the input is 1, and let's just assume it's staying 1 for a while so you can see how it's generating the 2400 hertz audio that's going out to the cassette player. So we're in this loop right here where it says it is 1, and we wait for the timer tick to actually occur. This is the hardware timer, so we always start at the exact same time. And of course, all the code we're going to execute will always take less than 13 microseconds so that we can get back here and wait for another tick to occur. All right, so let's say that tick has occurred. We clear the hardware, and then we look to see if we're still receiving 1. And I'm saying by definition here, yeah, we're still receiving 1. So it's going to decrement the period counter. This is going from 16 down to 0. And as long as it's not 0 yet, it's going to loop back here and do it again. So this will go through 16 times. That's half a cycle, 2400 hertz. And then it will finally fall out the bottom of the loop where it toggles the output from high to low or low to high, and then reloads the period right here back to 16 and repeats it. So this will just sit here and do 16, 13 microsecond ticks over and over, toggling each time it reaches 0. And that will give us our 2400 hertz output. Now let's say that we get a data transition where the line goes from 1 to 0. So it's coming in here and it sees, yes, it actually is changed. It's no longer 1. We now jump to now 0, which is down here in the RS-232, or the zero loop. At this point, we have to determine the two states that we talked about earlier. One, are we about to finish a half cycle, but we're going to have to finish it a bit early? Or two, have we already started the next half cycle, so we just need to extend it a little bit longer? And we can do that by looking at the period counter. If you think about it, the period counter goes from 16 down to 0, so if it's up at 16 or 15 or 14, that means we just started the new one. In that case, we don't want to toggle, we just want to extend it. If, however, that counter is down at 2, 1, 0, something like that, we know that we're finishing a cycle. That's the one we want to stop early. So that's what this little logic here does. If it wants to truncate and end it early, it does that right here with these two. Otherwise, it just sets the period so that we have the full cycle period going on for the next half cycle that we're going to generate. And then we fall into this loop where we're generating the half cycle times for the 0 loop. Of course, it does the same thing. Once it sees that it transitions back to 1 right here, it just jumps up to now 1, which does the exact same thing for the most part, and either ends the cycle early or extends a cycle that's already begun. And that's basically it. That's how it stays in sync, and this ended up working really well. As far as the software goes that actually demodulates the data and sends that over to the serial interface board, rather than looking at the code itself, let me just illustrate how it works on this chart right here. We basically have an input capture setup that captures all rising edges. So it captures this one, captures this one, this one, this one, and you can always compute the time between two rising edges just by subtracting the previous input capture from the current one. So if we subtracted these two, we would come up with a time of 832 microseconds, which is a full bit time. We know that's a 0. If, however, we get half of that, that must mean we're in a 1-bit cell. Now, the only difference between 1 and 0 is here, we don't want to actually transition the bit output yet. We want to wait until here so that we're always transmitting the bit transition at the end of this bit cell that I have shown here. So when this comes in and we get a half cycle, we set a flag knowing it's going to be 1, and then another half bit later, then we do the bit transition. And that's how the demodulator works. All right, let's go ahead and turn on a machine and actually watch this work. Let's take a quick look at the hardware we're going to run in this. Primarily, we have this IO4 board made by Solid State Music. Again, that's the board that we have strapped to look just like the 88 SIO. That's part of the Altair cassette. Main difference this time is we have it configured to run at 1200 baud instead of 300. RS-232 cable from that goes to the rear panel where it loops right over to this RS-232 cable. That in turn is connected to a little cassette interface board that we have modified to run at 1200 baud. And then the audio connector on that in the rear comes over to our cassette player. So the playback from the cassette player goes to the audio in jack, and here is the cable that's connecting the RS-232 output of the serial interface board over to that modem board. All right, other than that, I have a 88 2SIO drop-in replacement. That's going to be our console serial port. I got a RAM and EEPROM board, and then of course the CPU and front panel interface. Let me put a lid on this and we'll get this demo going. All right, go ahead and turn on the computer, give it a reset. We're going to use the multi-boot loader PROM, so we don't have to toggle in a loader on the front panel. That's at FE00. Then we need to tell BASIC what our serial port's going to be. That's a 2SIO. And we need to tell the loader what type of port to load through. That is the standard Altair cassette with no changes whatsoever there. All right, let me start the tape playing and hit run. Up here, I have a stopwatch running on my iPad. That way we can see how long this actually takes to load without having to sit here and watch that whole thing happen. So we'll come back in just a minute and see how long this took. Hopefully it takes just a little bit over a minute, maybe a minute and 10 seconds or so. That will be, again, 4 times as fast as the original, which takes just shy of 5 minutes. All right, this should be winding up soon. We'll see the light pattern change, and we'll see it pop up over here on the terminal. That'll give the memory size prompt over there. That'll let us know we've made it. Let's hope this works. And there we go. So just under a minute and 10 seconds, and we were up and running. All right, let me stop the tape player for now. All right. So as you could see, that process was identical to the way we've always done it. So nothing about the fact that this is 1200 baud changed anything about how you load BASIC. Hit return for memory size, terminal width, say yes. Okay, we're up and running 8K BASIC. Now there's no program in here right now, but I could load something off of tape. The way you would do that would be with a C load, and I have a CRAPS program sitting here next on the tape. And again, this is identical to how I would do it with the regular cassette interface. So the fact that we're using a drop-in equivalent that we made doesn't change a thing, and the fact that it's 1200 isn't changing a thing. So let me hit play on the tape. I'll hit return here. This loads in about 20 seconds as opposed to a minute and 20 seconds. Again, 4 times faster. All this is just, quite a bit nicer having it quicker. Now, unfortunately, this is not a project somebody could have done in the old days, like many of the things I've done that could be. This one obviously would be a fairly major job to make your own cassette. Okay, that's done already. So you can see how nice and quick that was. You don't have to head out too long in order to get programs loaded, get BASIC loaded, stuff like that. I mean, that's a decent sized program, about 2.5K. Now let's bet some money. What do you know, I lose. Hey, 120. Okay. Anyway, so again, it works just like the original, no changes, just 4 times as faster. But again, the fact that I did this so simply is solely because it's a modern design that I can just change the firmware in that little PIC processor on the modem board. Any real modem board change that you would have done back in the days would have been fairly complex, sort of like designing the CUTS board that you saw or the Altair cassette board, that kind of thing. But anyway, it was still a fun little project to do. I actually have one more thing I'm going to try with this. I'll look at this in the next video. Leaving all the same waveforms, but basically just encoding the data with MFM, which is what happened on floppy disks when they went from single density to double density. And again, the way this records is very similar to floppy disks. I should be able to get 2400 baud out of this using the same 2400 and 1200 hertz frequencies. So I may try that in the next video. I know there's going to be a couple of catches, but I think I can get around them. So maybe that'll be next.